This is a follow-up to my first video, and in it I discovered some new things I hadn't accounted for. After the first video, I built a 3D printed proof of concept model and ran water tests on it. A few things came out of that, some prompted by comments, some just from watching water move through a real object instead of a CAD screen. This chapter covers what I found. In this new reconstruction, the rope and roller system never gets wet. So why does the water stop there? In my reconstruction, the antechamber is a sealed space. There's no way for air to escape upward. Water can still pass through into the king's chamber. But that doesn't affect the antechamber's own cap. The air trapped above the antechamber still has nowhere to go, regardless of what's happening downstream. As water rises into a sealed chamber, it compresses the air above it, and the water level stalls once that trapped air pushes back hard enough to stop it. That's a pressure cap, not a chamber simply running out of room. I'll be honest, this specific sealed pocket behavior isn't something I'd thought through before. I do know how water caps work in general, but this particular case, two sealed spaces connected the way these are, wasn't something I'd considered until I built the physical model and watched it happen. Now, the red block itself. It doesn't fully submerge, and it submerges less than I first thought. The waterline sits inside the rectangular body itself, not at the rectangle to triangle divide like I originally assumed. The dry zone includes part of the rectangular body, the full triangular tip and the throw holes. Working from the block's measured dimensions, the submerged fraction comes out to about 78% of the block's total volume. The dry zone is about 22%, enough to meaningfully shift the buoyancy figure, not just nudge it. Direct calculation from the submerged geometry puts the buoyant force at roughly 765 kilograms force. One more detail from the model. The 4 through holes in the block, the rope attachment points, adjusted from 10 to 7.5 centimeters in diameter in this reconstruction, sit well above the waterline too, up at the rectangle to triangle divide. So the entire rope interface, tip and holes alike, stays clear of water. The block separates into a wet zone, doing the buoyancy work, and a larger than expected dry zone doing the rope work. The core reconstruction from the first video still holds. This is the model catching a real error in my own numbers before I locked them in. That's exactly what building the thing and testing it with water is supposed to do. Everything in this chapter assumes the antechamber is airtight. That's the working assumption behind the pressure cap I've described. It's possible it isn't airtight. If air could escape upward through the block holes or elsewhere, the pressure cap wouldn't hold the way I've described. That's a separate question, for another time.